In this lecture, we are going to discuss the details of indirect lighting that you will need to implement homework 3. Indirect lighting is the core of path tracing and global illumination which is required for photorealistic rendering. We seek to support multiple bounces of light and color bleeding. These images show what you can do with indirect lighting. Here is the light source with 0 bounces. This is the direct lighting. Putting together the light source and the direct lighting, you get this image. Here is the image with indirect lighting where you have 2 bounces, or sometimes we refer to it as 1 bounce indirect. The light from the light source hits one surface, another surface, and then the viewer. Taking indirect lighting into account, you get a brighter image that captures effects such as the interreflections and indirect light on both the red and the green walls. You can also have higher bounces of light, and after some number of bounces, the intensity starts decaying. Our goal is to support general paths and general visual effects. Here I've shown this famous Cornell Box Scene, where you can see that the images with direct lighting look much worse than the images with full global illumination that include indirect lighting. With indirect lighting, we get these nice effects, nice soft shadows, nice color bleeding onto the red wall as well as the green wall, the color bleeding from the walls onto the faces of the box, as well as the small box. You get the reflection of the sphere in the smaller box, and all of these effects are obtained with indirect lighting and global illumination. In general, we support paths that can have multiple bounces between the light source and the camera. Putting it all together, you can create images like this. This is the iconic image from the rendering equation paper. You notice that you get caustics below the glass balls where specular light is focused onto the diffuse surface. You get color bleeding from the base polygon that supports color on the objects. And all of these effects are done in a unified framework based on the rendering equation. That paper also introduced path tracing and importance sampling, which are the key aspects of what you will be doing in homework 3 and later in homework 4. Let me review the reflection equation. The reflected light, or the output image, is a sum of the emission from the light sources. In most cases, the emission term will be 0 unless you're at the light source. We then add in the integral of the incident light from the light source times the BRDF times the cosine of the incident angle. In the rendering equation, instead of assuming you know the incident light, it's a chicken and egg problem where the incident light depends on the reflected or the outgoing light from some other scene surface x prime, which you hit corresponding to the outgoing direction. So the reflected light on the left-hand side is unknown, but the reflected light on the right-hand side inside the integral is also unknown. Let's now get to the details of the assignment. First, I just want to point out a couple of minor changes in notation if you're looking at the assignment and trying to make the correspondence with the rendering equation we've discussed. The reflected light is the emissive light plus the integral as before. Now we have the BRDF, the cosine term, and the integration over the solid angle. However, the incident light, or correspondingly the reflected light from x prime, there's a slight change in notation. So x prime is just equal to this t of x comma omega in is the ray casting function to the first intersection. And we consider the outgoing light in the direction minus omega in from that location. We now need a Monte Carlo estimator that doesn't integrate over an area light source, but integrates over the entire hemisphere. In order to do that, we randomly generate a sample on the hemisphere, and the hemisphere corresponds to a total of 2 pi steradians. Therefore, the probability of generating any point on the hemisphere is 1 over 2 pi. When you divide by that probability, you end up multiplying by 2 pi here. You divide by the number of samples to normalize, and inside the summation, you have an estimator which is essentially the corresponding term in the integral. So the reflected light, here we have denoted omega I as a function of k, which corresponds to the omega I for the kth sample. Notice that you're drawing different samples on the hemisphere. For each of your samples, you have a different incident direction. So you multiply by the BRDF and the normal. That's simple enough, but by itself it's not ideal because you are calling LR, which is unknown, and the way you do that is with a recursive call. If you have a large number of samples at each bounce, you can quickly lead to an exponential increase in the number of rays or the number of samples or the number of paths, and therefore you need a termination condition. For now, just as in your ray tracer, set a fixed depth d is equal to 5 to guarantee that you terminate. Finally, instead of considering this exponential expansion, just consider a single path after splitting. In effect, you consider n is equal to 1, so that when you trace a path from the eye, there is only one subsequent ray that comes out instead of a large number of rays. You can then average over all the n samples going into the pixel. Or alternatively, you can say that the primary visibility is still computed with n samples, but subsequently each of those samples has only one ray or one path that they take going forward. Alternatively, you can think about this as rendering n images, each with one sample and one path per pixel, and then averaging. In fact, this corresponds to having a single path versus a bushy tree. So a bushy tree would be something like this, where you start with a single path to a triangle, and then at each bounce you split into 3 paths in this case, and so eventually you will have a large number of paths coming out of that single path. On the other hand, a single path, it hits the triangle and it continues with only one path going forward. So conceptually, it's simplest to render n one-sample images and then average them. Notice if you do this and each of the n images, instead of going through the center of the pixel, actually picks a random location on the pixel, then you get anti-aliasing within the pixel for free. So you consider the pixel having a unit area and you jitter within that instead of shooting the sample through the midpoint. You can see the effects of anti-aliasing. If you do your standard ray tracing, you will get the jaggies shooting through the center of the pixel, whereas if you do anti-aliased rendering, this will look much nicer.